Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. Today we'll be presenting our topic titled Application of Lagrange Multipliers. Lagrange multipliers is an important concept in multivariable calculus that help us find maximum or minimum values of a function where there is a constraint involved. In this presentation, we will explain the concept through a real-world problem, so it is easier to understand and relate to practical situations. The presentation is prepared by our group members. The members consist of Wan Anis Sumaira, Amal Isha, Isha Maridia, and also Filza Maisara. Each of us contributed to understanding the theory, solving the problems, and preparing this presentation slide. To begin, let us consider a real-life situation. Imagine a farmer who wants to build a fenced area beside a river. The river already acts as a natural boundary, so fencing is only needed on 3 sides. However, fencing is expensive, and the farmer only has 300 meters of fencing available. The main question here is how can the farmer enclose the largest possible area using this limited fencing? This is a perfect example of a constraint optimization problem, which can be solved using Lagrange multipliers. Now, let us define the problem mathematically. Let x be the width of the enclosure, which is perpendicular to the river, and let y be the length of the enclosure, which is parallel to the river. The area to be maximized is given by A equal to x multiplied by y. Since fencing is only needed on 3 sides, the constraint is 2x plus y equal to 300. This equation represents the limited amount of fencing available. Our goal is to maximize the area while satisfying this constraint, which is why we apply the Lagrange multiplier methods.
And now we will talk about the mathematical formulation, and the basic idea of it is to convert a constraint problem into a form such that the derivative test of an unconstrained problem can still be applied. So there are 2 important elements in the mathematical formulation, which is first the objective function, which is to define what we want to optimize, either it is maximize or minimize, and the example of it is max fxy. And then second is constraint, which is to define the limitations or conditions of the problem that must be satisfied. So the example of it is hxy equal to k. So next is the Lagrange multiplier derivation. So as we all know, Lagrange multiplier is a strategy to find the local maximum or minimum of a function subject to the constraint. So the relationship between the gradient of the constraint and the gradient of the function will lead to a reformulation of the original problem. So for example, we want to optimize the function f subject to function g equal to 0. So the first condition, which is the constraint condition, so any allowed change that stays on the constraint must satisfy dg equal to gx dx plus dy dy equal to 0. So we can say that dx dy is perpendicular to the gradient g. And then the second condition is the extremum condition. At the maximum or minimum on the constraint, the change in f along the constraint is 0. The f equal to fx dx plus fy dy equal to 0, and we can say that dx dy is perpendicular to the gradient f. So since the same dx dy now is perpendicular to both gradients, so the gradient must be parallel, and we can see that gradient f equal to lambda gradient g.
So in my part, I will solve the numerical example from this question, which is about maximizing the area of a rectangular enclosure built beside a river. Since one side along the river is not required, therefore fencing is only 3 sides of the rectangle. Also, we are given that the total length of fencing is 300 meters, and our objective is to find the dimensions that give the maximum possible area. To solve this problem, we use the method of Lagrange multipliers. First, we define the objective function, which represents the area of the rectangle, which is f equal to xy, and we define the constraint function based on the fencing length with equation g equal to 2x plus y equal to 300. Next, we calculate the gradients of both functions. The gradient of every function is yi plus xj in vector form, and the gradient of the constraint function is 2i plus j in a vector form also. Then, according to the Lagrange multiplier method, the gradient of the objective function must be parallel to the gradient of the constraint function. So it's represented in this equation, which is gradient f equal to lambda gradient g. So substituting the gradients, we obtain yi plus xj equal to lambda in the bracket 2i plus j. Next, we compare the component and get y equal to 2 lambda and x equal to lambda. And then substitute this expression into the constraint equation, we get lambda equal to 75. Now we substitute the value of lambda back into the equation of 4x and y. We get x equal to 75 and y equal to 150. Finally, we can calculate the maximum area by substituting this value into the area formula, which is a equal to xy, and then we can get a equal to 75 times 150. We get a equal to 11,250. Therefore, the maximum area is achieved when the length of fencing perpendicular to the river is 75 meter and length parallel to the river is 150 meter. This confirms that the Lagrange multiplier method successfully determines the optimal dimensions under the given constraint.
For my part, I will be concluding today's problem. This problem applied the method of Lagrange multipliers to determine the maximum possible area of a rectangular enclosure built beside a river with a fixed amount of fencing, that is 300 meter. The area depends on two variables, which consist of x, that is the width perpendicular to the river, and y, the length parallel to the river. These variables are linked by the fencing constraint, which limits how large the enclosure can be. Besides, this problem is a constraint optimization problem, so the variables are not independent. From the calculation, the optimal dimensions were found to be 75 meter for each side perpendicular to the river, x, and 150 meter for the side parallel to the river, y. This result shows that the length parallel to the river is twice the width. This 1:2 ratio is a fundamental characteristic of three-sided optimization, while a square 1:1 ratio is ideal for four-sided enclosure. The missing boundary of the river allows more enclosure of the land in 1:2 ratio with the same amount of fence, resulting maximum area which is 11,250 meters square. Compared to when using 1:1 ratio, we will get 100 meter each of the side, resulting to the area which is 10,000 meters square. That is not the optimal area of the fence. By using the constraint correctly, the enclosure dimensions give the largest area were identified. This problem clearly bridges the gap between the abstract, calculus, and real-world efficiency. Overall, the objective of maximizing area within limited resource was successfully achieved. On to the last part, which is limitation. This method of Lagrange multipliers has identified the maximum area. However, this analysis is based on several simplifying assumptions. It is divided into three. The first one is, it assumes that the land beside the river is flat, rectangular, and fully usable, which may not always be true in real situation. The second one, the model also assumes that the fencing material is flexible, uniform in cost, and can be placed without restriction. Lastly, environmental factors such as the river curvature, soil condition, and safety setbacks are not considered. These factors could affect the actual enclosure size and shape. Therefore, while the mathematical model provides an ideal solution, adjustment may be needed when applying it to real-world conditions. That is all from us. Thank you.